Hey everybody, welcome to the Fischer Esterification lab. Here's the outline for this video. I'll be going over the reaction and mechanism and then walking through the procedure, going over the techniques involved, and I'll spend some time talking about some characterization techniques. I also want to give a brief introduction to the lab, showing where things are, what you're expected to bring, and stuff like that. And finally, I'll show the actual experiment in the lab. Here's the reaction that we'll be doing. We'll be taking acetic acid and reacting it with isopentyl alcohol using sulfuric acid as the catalyst to form isopentyl acetate, commonly known as banana oil because it smells like bananas. I think it smells like banana Laffy Taffy, which is kind of cool. And then notice that inorganic water is also a byproduct of this reaction. This is the mechanism pulled from the procedure, and it's a general mechanism using arbitrary R groups on the compounds to represent some carboxylic acid reacting with some alcohol, but can be applied to our specific compounds like acetic acid reacting with isopentyl alcohol. Initially, acetic acid is activated by sulfuric acid to create a better electrophile, which is susceptible to nucleophilic attack from the isopentyl alcohol. This creates an unstable tetrahedral intermediate, and when that collapses, water is kicked off, the carbonyl group is reformed, and the ester product is produced. As you can see, this reaction is in equilibrium because the water can react with the ester product formed, hydrolyzing it back into the two reagents. So we can use Le Chatelier's principle to form more product by manipulating the water. If water is removed during the reaction, that'll place stress on the side of the products, driving the reaction towards the product. One way to do this is to use silica gel beads, which are commonly used in packaging because they absorb water. So we'll place them in the conical vial with the other reagents, and as the reaction is taking place, they'll absorb the water as it's produced. Another way to monitor the amount of water in the reaction is to use sulfuric acid as the catalyst rather than other commonly used acids. Other acids in the lab are dissolved in an aqueous solution, so if we use them instead, we'd be introducing a bunch of water into the reaction vessel. Whereas we can get sulfuric acid without any aqueous solution, therefore avoiding that problem. We'll also place a drying tube on top of the apparatus filled with calcium chloride, which is a desiccant salt that absorbs water. And the reason that we want it attached to the apparatus is because there's moisture in the air, and it'll absorb that water, preventing it from entering the conical vial and driving the reaction towards the reagents. We'll allow everything to reflux for about an hour, and that is a common technique, sometimes called a rolling boil, because we want to boil the compounds in order for them to reach the activation energy required for the reaction to happen. But we don't want to just boil everything off, so we need a way to condense the vapors in order to not lose the product that we're forming. To do this, we'll be using a water condenser during the reaction. So here's the conical vial where the reaction will be taking place, and attached above will be the water condenser. It has a hollow inner tube that goes all the way through and an outer tube that is attached to a water source. So water will flow in from the bottom and then come out the top, filling the outer tube with cold water. And then as the reaction takes place, vapors will rise up into the hollow inner tube of the water condenser, interacting with the cold surface of the glass, so they'll condense back into their liquid form and move back into the reaction vessel so we don't lose anything during the reaction. Once the hour reaction is done, we'll work on isolating the product by removing any leftover reagents and any leftover catalyst. To do that, we need to know which reagent is in excess, so basically we need to figure out which one is the limiting reagent. So let's take a look at the table provided in the procedure. In this table, we have the list of all of the compounds used or produced in this lab, along with the safety concerns attributed to each compound. Then we have their molecular weights, the weight or volume used of each compound, and it's really nice because that weight and volume has been converted into millimoles for us. Now in this reaction, since it's a 1-to-1 ratio from each of the reagents to the product, whichever reagent has a smaller amount of millimoles used, that'll be the limiting reagent. So in this case, it would be isopentyl alcohol. This means that the alcohol should be used up completely in the reaction, and acetic acid will be what's left over and in excess. This is actually done on purpose because the product will be more easily isolated if acetic acid is what is in excess rather than isopentyl alcohol. And this is because acids can be more easily moved into an aqueous layer, removing them from the organic one where the product is. This is done by using some base to deprotonate the acid, ionizing it so that it'll want to move into the polar aqueous phase. In this case, we'll be using sodium bicarbonate, which when it reacts with the acid will turn into water and CO2 gas. So when the sodium bicarbonate is added, we'll see two layers. The top layer will be the organic layer since isopentyl acetate is less dense than water, and the bottom layer will be the aqueous layer containing the sodium bicarb. And as those two layers are mixed together, we'll see CO2 bubbles coming off as the sodium bicarb reacts with any excess acid left over. And we'll rinse that organic layer a total of 3 times just to make sure that the sodium bicarb is able to react with all of the acetic acid as well as the sulfuric acid catalyst. Since we're doing this with a Pasteur pipette, there's no way that we're going to be able to get rid of all of the water before moving on to the next steps. So we need a way to dry the organic layer in order to remove any water that would be left over after doing those 3 rinses. To do this, we'll be using sodium sulfate, which is another desiccant salt because it absorbs water. So initially when the sodium sulfate is added to the organic phase, it'll begin to clump up as it absorbs the water. But as we continue to add it, the salt crystals that are added will no longer clump up with the already existing larger clumps because there's no more water to absorb. The larger clumps will still exist because that's where the water is, but the other salt crystals will move around freely on their own since the organic phase is now dry, and this is called free flowing. Here's an example of what free flowing would look like in a colored solution, just so that we can see the sodium sulfate a little bit clearer. And it'll actually be easier to see looking at it from the bottom, so I'll show it to you like that. But here you can see the larger clumps where the water has been absorbed, as well as the free-flowing crystals, indicating that this solution is dry and free of water. Once we have our dry product, we're going to distill it to help purify it from any remaining contamination. For example, if there was any isopentyl alcohol left over from the reaction portion, we'd want to remove that so we can characterize a pure product. So basically, distillation will help us separate 2 miscible compounds based off of their boiling points. This is what the apparatus will look like during the distillation process. Here we have the conical vial where we'll be boiling the product, and the water condenser just to make sure that the vapors do condense as they come off. And then in the middle will be the Hickman still, which has a wider portion on the bottom. So as the vapors condense and move down the glassware, the liquid product will gather in this portion here, and then we can just take off the cap and remove the product from the Hickman still using a Pasteur pipette. And the idea with distillation is that the contamination would have a different enough boiling point from the product that it would get left behind in the conical vial as the product boiled off, or vice versa, therefore separating one from the other. During this process, we'll also be measuring its boiling point as a way to help characterize the product. So we'll place a thermometer through all the glassware just above the boiling liquid so that we can measure the temperature of the vapors as they come off. Here we'll be looking for a lag in the thermometer around 142 degrees Celsius since that's the boiling point of isopentyl acetate, but it'll probably be a few degrees lower since we're at a higher elevation here in Utah. That temperature lag comes from this diagram where we have our liquid, and initially the heat and energy that we put into that liquid goes into rising the kinetic energy of those molecules, so the temperature will go up, but eventually it'll reach the boiling point where the energy is now going into the phase change, turning the liquid into a gas, and the temperature should stay pretty steady here, so we'll measure that as our boiling point. Once that's done, we can work on characterizing the product, and we'll do this in multiple ways. Since it's a liquid, we can take its boiling point, which we just did. We can also measure its refractive index. If you remember from your physics classes, the refractive index is a measurement of how much the speed of light changes as it goes through different mediums. Since different liquids have different densities, they'll refract light uniquely enough that we can use their refractive indices to characterize the different compounds. So this is what the reading will look like from the machine, and we can take that value and compare it to the literature values provided on the table. For our product, the isopentyl acetate, we're expecting its refractive index to be around 1.4000. And the last technique that we'll talk about is called infrared spectroscopy, which basically just shines infrared light through some compound, and certain frequencies of that light are absorbed as they interact with specific bonds on the molecule. So here's an example IR spec that was taken for isopentyl alcohol, and we can actually figure out what functional groups are on the molecule based off of the absorption pattern that we see. You can start learning where these peaks will show up for specific functional groups using handouts like this that are on Learning Suite, but your job will be to analyze the IRs taken for each product and label the peaks according to the functional groups that are on that product. For example, this wide peak here would be for the OH group. This grouping of peaks would be for the carbon-hydrogen bonds for carbons that are sp3 hybridized. This grouping of peaks would be for the carbon-carbon single bonds, and then this peak here would be for the carbon-oxygen single bond. This is what a correctly labeled IR should look like, and this would be great if isopentyl alcohol was our product. Now, it's not as pertinent to label all of the carbon-hydrogen and carbon-carbon single bonds because they're not particularly unique to our product, but it's still good to know where they show up. If this was the IR run for the actual product, the isopentyl acetate, then we'd have a problem because there's no peak for the carbonyl group, and this molecule doesn't have an OH group, so the OH peak would have to be coming from some contamination, likely unreacted isopentyl alcohol left over, and we would want to label that as contamination. If this was the IR that we took for the product, then I would say that we actually didn't isolate the product because this doesn't match up very well at all. We'll also weigh out the product so that we can calculate a percent yield for this reaction, and then we'll use the limiting reagent to calculate a theoretical yield and divide the actual yield that we get in the experiment by the theoretical yield, multiply that by 100, and that'll give us the percent yield. When you come down to the lab, there are lockers in the hallway where you can store your backpack, jacket, or other items that you might have with you. Once inside the lab, a drawer should have already been checked out to you, so you can go ahead and open that up, and then you can use the lock to secure your items in the locker outside in the hallway. All of these items will be given to you on the first lab day. They'll just be by your station, and we'll be using them throughout the semester, so before doing anything, make sure to put them into your drawer before you forget. You will need a lab coat and goggles every time we're in the lab, and you're actually not allowed to do the labs without the proper personal protective equipment. So if you don't have these items, you can walk down to the chem stores in the Nichols building where you'll be able to purchase both the lab coat and the goggles. And then you can store them in your drawer after each lab period so that you don't have to be carrying them around. You will also need to wear long pants and closed-toed shoes whenever in the lab. You won't be allowed in wearing shorts, sandals, or anything that'll expose you to chemicals. Gloves should also be worn during the experiments, and those will be found at the front of each lab. Also at the front will be the reagents, solvents, and other compounds used throughout the labs, and they are organized on the top shelf by experiment. So for this experiment, we'll look for the Fischer Esterification label and use the reagents found there. And then the bottom shelf has the solvents or other compounds that are commonly used throughout each lab. When dispensing the reagents, please be respectful to other students. Don't take the bottle to your personal lab station where students won't be able to find it, and cap the reagents and solvents whenever they're not being used. If we need to use a stronger acid or base or a more hazardous volatile material, those will be found in the hood, and the bottles for those compounds should remain in the hood. And then in the back of the lab, there are other items that are available for students to use, like weigh boats, pasture pipettes, test tubes, and surgical tubing. When performing the labs, your lab station should be clean and organized with only the items being used in the experiment and your lab notebook, which should have the procedure already written down and all of the pre-lab assignments completed, which are highlighted in red in the lab write-up format sheet. While in the lab, we ask that you not use your phone to be texting, to watch videos, or for social media. But if you have your phone out to be looking at the post-lab questions and working on those while the reaction is going, that is totally fine. As for the witness signature from one of your TAs, that'll kind of just depend on the semester and what your instructor says. Okay, now that we've gone over some lab basics, let's go into the actual experiment. I'll be using a serological pipette to get the liquid reagents, and I'll attach it to a syringe using some tubing, like this. And now I'm ready to start dispensing the reagents. I'll first add 1.5 milliliters of isopentyl alcohol to a 5 milliliter conical vial with a large spin vane. Then I'll go over to the hood where we store the more hazardous or volatile compounds. So here's where I'll find both of the acids for the reaction. In the hood, I'll dispense 830 microliters of the glacial acetic acid, as well as 4 drops of the sulfuric acid to catalyze the reaction. Then I'll weigh out about 100 milligrams of the silica gel beads to absorb the water, and place that in the 5 milliliter conical vial as well. Now I can start setting up the apparatus, and here's a look at the water condenser. To set that up, I'll grab some surgical tubing from the back of the lab, and only 2 will be needed for each student. I'll attach the surgical tubing, the source of water being attached to the bottom, and the top tubing going out into the sink. Then I'll attach it to the conical vial, and as I turn on the water, you can see it flowing through the bottom of the water condenser and coming out the top. And the water can be turned on pretty gently. We don't need it blasting out of the tubing, just flowing through the water condenser. Here's the calcium chloride that will be used to absorb any water in the air. So I'll get some of that out and place it into the drying tube, holding it between 2 pieces of cotton. I'll attach that to the top of the water condenser, and now I can start heating up the conical vial, and I'll want to get the reagents boiling so that we can start the hour reflux. Here's a good example of what refluxing looks like. You can see the liquid boiling and the condensation gathering on the sides of the glass and rolling back down into the conical vial. Once the hour has passed, I'll take the apparatus off of the heat so things can cool, and I'll remove the drying tube so that the calcium chloride can be disposed of in the desiccant waste. Then I'll just move the product over to a clean conical vial to separate it from the silica gel beads, and I'll start the sodium bicarb rinses, gathering some in a separate beaker. And as it's added, you can clearly see the CO2 bubbles coming off as it reacts with the sulfuric acid and the acetic acid left over from the reaction. As that settles down, I'll make sure to mix the 2 layers together really well to help the base react with everything in there. Then the bottom aqueous layer can be removed, and I'll just repeat this process 2 more times. While that's going, I wanted to talk about extraction theory, which isn't exactly what we're doing here, but we'll do extractions plenty in future labs. So let's say we did some reaction, and after we are left with an aqueous solution that contains both our desired organic product, but also some byproduct, maybe inorganic or some other organic molecules that we don't want. So what we'll end up doing is add an organic solvent that is not miscible with water so that we can create a bilayer. In this lab, we usually use methylene chloride or diethyl ether. Now we want to choose an organic solvent that is more miscible with or dissolves the organic product better than water does, so that when we mix the 2 layers and allow them to separate, the organic product will move into the organic layer. And then we can remove the aqueous layer with the byproducts, and that will hopefully leave the organic layer with just our desired organic product. In future labs, we'll do this in our conical vial. We'll add an organic layer, some solvent, and mix it with our aqueous layer really well. And this will help pull the desired product up into the organic layer, removing it from the aqueous one. I'll remove the aqueous layer for a second time and then perform one more sodium bicarb rinse. Finally, I'll do one wash with some distilled water to help remove any sodium bicarb that might have been left over. Once those are done, I'll transfer the product to an Erlenmeyer flask where I can then add the sodium sulfate to dry it, and I'll be adding that until it's free flowing. And it's a little more difficult to see here than in the colored solution, but there are individual crystals in there that aren't clumping up with the other ones, so this is free flowing now. I'll remove the product from the sodium sulfate and start setting up the distillation apparatus. I'll make sure to add the thermometer so that we can measure the boiling point, and I'll place it just above the liquid. Now we can start heating up the conical vial until the liquid starts to bubble. And if we take a look at the thermometer, it's still rising in temperature, so we're not going to record the boiling point quite yet. But now the product is really starting to boil, and we can even see it gathering in the Hickman still as the vapors start to condense. At this point, the thermometer looks like it stopped going up in temperature, and it's kind of hard to see, but it seems to be right around 136 degrees Celsius. The product has been completely boiled off now and is gathered in the Hickman still, so I can start gathering that. But before doing so, I'm going to weigh out an empty dram vial so that we can calculate a % yield later. And I'll transfer the distilled product into that dram vial using a Pasteur pipette. Then I can weigh out the full dram vial to get the weight of the product isolated in this reaction. Now I'll characterize that product first by running an IR spec, and here are the salt plates used to suspend the liquid in the spectrometer. I'll place a little bit of the product on one of the salt plates using an open capillary tube, and as they are placed together, you can see the product now suspended in between them. I'll put them into the spectrometer to run the IR spec now. And it turned out pretty well. We can see the carbonyl peak around 1740, 2 carbon oxygen peaks for the ester, one around 1245 and the other around 1050. And it does look like there's a little bit of OH contamination, but it's pretty small. Finally, I'll measure the refractive index. So I'll rinse off the machine using some ethanol, just in case there's some previous product left over. And then I'll spot the crystals with a little bit of our product, making sure just to add enough to line that crystal. Then I'll close the machine and bring the light up. As we look through the microscope, we can see a light and a dark hemisphere, and I've adjusted it so that the line separating those two hemispheres is right in the middle through the crosshairs. Then when I turn off the light, we can see the actual values, and we'll want 4 significant figures after the decimal point, so the refractive index for this product isolated would be 1.3994. Here at the end, I just wanted to show you real quick how we would clean up and dispose of all the chemicals. So in the hood, we have some buckets where we dispose of the chemicals used. On the left side, we have the aqueous waste bucket, and that's where we'll dispose of all of the sodium bicarb rinses, the distilled water, and anything that is an aqueous solution. Then on the right, we have the organic waste bucket, so that'll be for any leftover product or organic solvents that were used throughout the reaction. And the calcium chloride, the sodium sulfate, and the silica gel beads will all be disposed of in the desiccant waste. Then to clean the glassware used in the lab, we use acetone because it dissolves a wide range of organic compounds, plus it's miscible with water. So I'll add that to the glassware used, switch it around, and can even use that same acetone to rinse a different container. And finally, I'll put the surgical tubing back so that students in future labs can also use it.